Tonight, we're going to talk about something hiding inside every atom in your body. The neutron. You've probably heard of it. You learned about it in school. It's the neutral particle sitting in the nucleus alongside the proton. Simple, right? Except it's not simple at all. Because here's what most people never learn. A neutron, left on its own, outside the safety of an atom, will die. It will fall apart in roughly 10 minutes. It literally cannot survive alone. And when you discover why, when you understand what a neutron actually is beneath the surface, and what's really happening when it decays, it opens up one of the most stunning stories in all of physics. One that connects quarks, forces of nature, and the very reason matter exists at all. Before we go any further, if discovering what truly lies inside matter sparks your curiosity, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now settle down and make yourself comfortable. Let's begin. Let's start with something you think you already know. The atom. You learned about it in school, maybe in middle school, maybe in high school. You saw that diagram, the one with a cluster of balls in the center and smaller balls orbiting around it like tiny planets. The teacher told you the cluster in the middle is the nucleus, made of protons and neutrons. The little things orbiting around it are electrons. Protons have a positive charge. Electrons have a negative charge. Neutrons have no charge at all. They're neutral. That's why they're called neutrons. You probably memorized this for a test, answered a few questions about it, and moved on with your life. And honestly, for most purposes, that picture works fine. It's good enough to explain chemistry. It's good enough to understand why certain elements behave the way they do on the periodic table. It's good enough for everyday life. But here's the thing. That picture is not just incomplete. It's almost entirely wrong about what's actually going on inside the atom. Not wrong in the sense that it gives you bad answers for chemistry class, but wrong in the sense that it hides something far deeper, far stranger, and far more beautiful than most people ever get to see. Let's go back to that nucleus for a moment. You were told it contains protons and neutrons. And that's true. A hydrogen atom has 1 proton and no neutrons. A helium atom has 2 protons and 2 neutrons. A carbon atom has 6 protons and 6 neutrons. An iron atom has 26 protons and 30 neutrons. The number of protons defines what element you're dealing with. Change the number of protons and you change the element entirely. The neutrons are there too, sitting alongside the protons, contributing mass but no electric charge. In school, protons and neutrons were presented as fundamental things, basic building blocks, the smallest pieces of the puzzle. You were told the atom is made of 3 particles: protons, neutrons, and electrons. And for a long time in the history of physics, that's what scientists believed too. The proton was discovered in 1919 by Ernest Rutherford. The neutron was discovered in 1932 by James Chadwick. The electron had been known since 1897 when J.J. Thomson found it. For decades, these 3 particles were considered the fundamental constituents of matter. Everything in the universe, every star, every planet, every person, every grain of sand was thought to be built from these 3 basic pieces. But starting in the 1950s and accelerating through the 1960s, physicists began discovering something troubling. They started smashing protons and neutrons together at high energies in particle accelerators And instead of finding simple, solid objects, they found a mess. Hundreds of new particles started showing up. Particles with strange names like pions, kaons, sigma baryons, and delta resonances. The list kept growing. Every time physicists increased the energy of their collisions, more particles appeared. It was chaos. There were so many particles that physicists started calling it the particle zoo, and it didn't make sense. If protons and neutrons were truly fundamental, why were all these other particles showing up? Why was the subatomic world so complicated? The answer came in 1964 from a physicist named Murray Gell-Mann, and independently from George Zweig. They proposed that protons, neutrons, and all those other particles in the zoo weren't fundamental at all. They were made of even smaller things. Gell-Mann called them quarks. The name came from a line in James Joyce's novel Finnegan's Wake, 3 quarks for muster mark. It was a deliberately playful, almost whimsical name for one of the most revolutionary ideas in the history of physics. But the idea behind it was deadly serious, and it changed everything we thought we knew about the nature of matter. According to Gell-Mann's model, protons and neutrons are each made of 3 quarks, not 1, not 2, 3, and these quarks come in different types, which physicists call flavors. There are 6 flavors of quarks in total: up, down, strange, charm, bottom, and top. But for understanding the neutron, we only need to worry about the 2 lightest flavors, up and down. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 2 down quarks and 1 up quark. That's the difference between them. That's all it takes to go from a positively charged proton to an electrically neutral neutron. Swap 1 up quark for 1 down quark. The up quark carries an electric charge of plus 2/3. The down quark carries an electric charge of minus 1/3. If you add up the charges inside a proton, 2 up quarks at plus 2/3 each gives you plus 4/3, and 1 down quark at minus 1/3 gives you minus 1/3. 4/3 minus 1/3 equals plus 1. That's the proton's charge, exactly plus 1. For the neutron, 2 down quarks at minus 1/3 each gives you minus 2/3, and 1 up quark at plus 2/3 gives you plus 2/3. Minus 2/3 plus 2/3 equals 0. That's why the neutron is neutral. It's not that it has no charged particles inside it. It has charged particles. They just happen to cancel out perfectly. This was a stunning revelation. The neutron, which everyone had thought of as a simple, featureless, neutral ball, turned out to be a composite object. It has internal structure, it has parts. It has a rich and complicated interior life that is hidden from view unless you know how to look. When Gell-Mann first proposed this, many physicists were skeptical. Quarks seemed like a mathematical trick rather than real physical objects. Some prominent physicists argued that quarks were just a bookkeeping device, a convenient way to organize the particle zoo, but not actual things you could find inside a proton or neutron. That debate was settled in 1968 and 1969 at the Stanford Linear Accelerator Center, known as SLAC. Physicists there fired high-energy electrons at protons and observed what happened. If the proton were a smooth, uniform blob, the electrons would scatter in predictable, gentle patterns. But that's not what happened. Some electrons bounced back at sharp angles, as if they had hit something hard and point-like inside the proton. This was strikingly similar to Rutherford's famous gold foil experiment from 1911, where alpha particles bouncing off gold atoms revealed the existence of the nucleus. The SLAC experiments revealed that protons contained small, hard objects inside them. These were quarks. They were real. Not mathematical fictions, not convenient bookkeeping tools, but actual physical constituents of matter that existed inside every proton and neutron. This discovery earned Jerome Friedman, Henry Kendall, and Richard Taylor the Nobel Prize in Physics in 1990. It was one of the most important experiments of the 20th century. So the neutron is made of quarks, 2 down quarks and 1 up quark. But what holds them together? Why don't the quarks just fly apart? After all, we know that like charges repel. 2 of the quarks inside the neutron, the 2 down quarks, have the same type of charge. And beyond that, quarks are incredibly small. They're crammed together in a space that's roughly 1 femtometer across. A femtometer is 1 quadrillionth of a meter. That's a decimal point followed by 14 zeros and then a 1. At those distances, you would expect any repulsive force to be extraordinarily strong. So something must be holding the quarks together. Some force powerful enough to overcome any repulsion and bind 3 quarks into a stable package. That force is the strong nuclear force, and it is, by a wide margin, the most powerful force in the known universe. Let me give you a sense of how powerful it is. The electromagnetic force, the force that holds electrons in orbit around atoms, that makes magnets stick to your refrigerator, that carries light from the sun to your eyes, is about 100 times weaker than the strong force. Gravity, the force you feel every day pulling you toward the ground. The force that holds the moon in orbit around the Earth and holds the Earth in orbit around the sun is roughly 10 to the 38th power times weaker than the strong force. That's a 1 followed by 38 zeros. The strong force is almost incomprehensibly more powerful than gravity. If gravity were a gentle breeze, the strong force would be a hurricane that makes every hurricane in human history look like a whisper. But the strong force is also weird. Very weird. It behaves in ways that are completely unlike any force you experience in everyday life. To understand how, we need to talk about something called color charge. In electromagnetism, the property that determines how particles interact with the electromagnetic force is electric charge. Positive and negative. Like charges repel, opposite charges attract. Simple. The strong force has its own version of charge, but it's much more complicated. Instead of 2 types, positive and negative, the strong force has 3 types of charge. Physicists call these 3 types red, green, and blue. Now, these have absolutely nothing to do with actual colors. Quarks are not literally red or green or blue. The names are just labels, borrowed from the color system because it was a convenient analogy. Each quark carries one of these 3 color charges. One quark might be red, another might be green, another might be blue, and just like in the color world where combining red, green, and blue light gives you white light, in the strong force, combining a red quark, a green quark, and a blue quark gives you a color-neutral particle. This is why protons and neutrons always contain exactly 3 quarks. You need one of each color to create a color-neutral combination. A particle that isn't color-neutral can't exist as a free particle. Nature demands that any observable particle be color-neutral. This rule is called color confinement, and it has profound consequences that we'll get to shortly. The particles that carry the strong force are called gluons. Just as photons carry the electromagnetic force between electrically charged particles, gluons carry the strong force between color-charged particles. But here's where things get radically different from electromagnetism. Photons are electrically neutral. They carry the electromagnetic force, but they don't carry electric charge themselves. This means photons don't interact with each other. Two beams of light can pass right through each other without affecting one another. Gluons are different. Gluons themselves carry color charge. They're not neutral. A gluon carries a combination of a color and an anticolor. Because gluons carry color charge, they interact with each other. They can emit and absorb other gluons. This creates a situation that has no parallel in electromagnetism. The force carriers themselves are subject to the force they carry. This self-interaction of gluons is what makes the strong force behave so strangely. In electromagnetism, as you pull two charged particles apart, the force between them gets weaker. Double the distance and the force drops to a quarter of its original strength. This is the familiar inverse square law. The strong force does the opposite. As you try to pull two quarks apart, the force between them gets stronger, not weaker, stronger. Imagine stretching a rubber band. The farther you stretch it, the harder it pulls back. The strong force between quarks behaves something like that, except far more extreme. The more you try to separate quarks, the more energy you pump into the gluon field between them. The gluon field forms something like a tube or a string connecting the quarks. As you stretch this tube by pulling the quarks apart, you're storing more and more energy in it. Eventually, if you put in enough energy, something dramatic happens. The gluon tube snaps. But instead of freeing the quarks, the energy stored in the tube creates new quarks. A new quark-antiquark pair pops into existence from the energy. You started trying to pull one quark free, and you ended up with more quarks instead. You can never isolate a single quark. No matter how much energy you use, no matter how hard you try, you will never see a lone quark sitting by itself. Every time you try to yank one free, the energy you use creates new quarks that immediately bind with the one you were trying to extract. This is color confinement, and it's one of the most remarkable properties of nature. Quarks are permanently imprisoned. They can never be alone. This has been tested experimentally many, many times. In particle accelerators around the world, at CERN in Switzerland, at Fermilab in Illinois, at Brookhaven in New York. Physicists slam protons and other particles together at enormous energies. When they do this, quarks inside the colliding particles are briefly knocked loose, but they don't fly away as free quarks. Instead, they immediately generate jets of new particles, streams of protons, neutrons, pions, and other composite particles spray outward from the collision point. These jets are the visible signature of quarks trying and failing to escape confinement. The quarks' attempt to flee creates a cascade of new particles, all of them color neutral, all of them composites of quarks. No free quark has ever been observed, and the theory of the strong force, called quantum chromodynamics, predicts that none ever will be. Let me try to give you a picture of what it's like inside a neutron, because it's nothing like what most people imagine. Most people If they think about the neutron's interior at all, picture 3 little balls sitting calmly in a tiny space. Maybe they imagine the quarks as 3 marbles in a bag, sitting still, touching each other, stable and quiet. That image could not be more wrong. The interior of a neutron is one of the most violent, dynamic, chaotic environments in the entire universe. The 3 quarks, the 2 down quarks and 1 up quark, are called valence quarks. They're the quarks that define what the particle is, but they're not alone in there. The gluon field that binds them is constantly fluctuating. Gluons are being emitted and absorbed at a furious rate. And because gluons carry enough energy, they can spontaneously create quark-antiquark pairs that pop into existence, and then annihilate each other almost instantly. At any given moment, the interior of a neutron contains not just 3 quarks, but a seething, churning sea of virtual quarks and antiquarks and gluons, all appearing and vanishing in a frenzied dance. Physicists call this the quark-gluon sea. Here's something that might truly surprise you. Most of the neutron's mass does not come from the quarks themselves. The up quark has a mass of only about 2.2 mega-electron-volts. The down quark has a mass of about 4.7 mega-electron-volts. If you add up the masses of 2 down quarks and 1 up quark, you get roughly 11.6 mega-electron-volts. But the neutron's total mass is about 939.6 mega-electron-volts. The quarks account for barely more than 1% of the neutron's mass. So where does the other 99% come from? It comes from energy. Specifically, it comes from the energy of the strong force itself. The gluons zipping around inside the neutron, the virtual quark-antiquark pairs popping in and out of existence, the kinetic energy of the quarks as they zoom around at close to the speed of light within their tiny prison. All of this energy contributes mass according to Einstein's famous equation E = mc squared. Energy and mass are interchangeable. The enormous energy of the strong force interactions inside the neutron manifests as mass. When you step on a bathroom scale and read your weight, almost all of that weight comes not from the quarks that make up your atoms, but from the energy of the gluon fields binding those quarks together. You are made mostly of energy, not matter in the simple sense. The solid, heavy feeling of your body, the heft of a rock in your hand, the weight of water in a glass, almost all of it is a consequence of the strong force doing its work inside every proton and neutron in every atom of your being. You feel heavy because the strong force is powerful, not because the quarks inside you weigh very much. They barely weigh anything at all. This is one of the most profound realizations in modern physics. The mass that we experience, the mass that gives substance to everything around us, is overwhelmingly generated by the dynamics of the strong force. It's not an inherent property of the fundamental building blocks. The quarks themselves are almost massless. The mass we feel, the mass that gives weight to the stars and planets and mountains and oceans, is a product of the strong force's furious energy, trapped inside particles so small you'd need a microscope 1 billion times more powerful than anything that exists to see one. Now, this brings up an interesting question. Where do the quarks themselves get their small amount of mass? Because even though it's only about 1% of the neutron's total mass, the quarks do have some intrinsic mass. That mass comes from a completely different mechanism, one involving the Higgs field. The Higgs field is a quantum field that permeates all of space. It's everywhere. You're immersed in it right now. Every particle that has mass interacts with the Higgs field, and it's this interaction that gives particles their intrinsic mass. The Higgs boson, discovered in 2012 at the Large Hadron Collider at CERN, is the excitation of this field. Its discovery confirmed that the Higgs mechanism is real. So the quarks get their small intrinsic masses from the Higgs field, but the neutron gets almost all of its mass from the energy of the strong force. These are two completely different sources of mass operating at two completely different scales. Let me give you another way to appreciate how extraordinary the strong force is. The range of the strong force is incredibly short. It operates only over distances of about 1 femtometer, roughly the size of a proton or neutron. Beyond that distance, the force effectively vanishes. Compare this to gravity or electromagnetism, which have infinite range. The gravitational pull of the sun reaches across billions of miles to hold the planets in orbit. Electromagnetic signals travel across the entire observable universe. But the strong force operates only within a space so small that you'd need to line up roughly 1 trillion of those spaces side by side to span the width of a single atom. Despite this tiny range, the strong force within that range is phenomenally powerful. It has to be. It's holding quarks together against their own kinetic energy, against quantum mechanical effects that try to spread them out, against everything that would tear them apart. And it does this effortlessly. The strong force doesn't strain to hold the neutron together. It dominates completely within its domain. This also explains why the strong force doesn't affect our everyday lives directly, even though it's by far the most powerful force in nature. Its range is so short that it's completely contained within atomic nuclei. You never feel the strong force because it never reaches beyond the incredibly tiny space inside protons and neutrons. It's like having the most powerful engine in the world locked inside a box too small to see. The engine is roaring, generating immense power, but it's all happening on a scale so small that we don't notice it. There's something else happening inside the neutron that's worth understanding. The quarks aren't sitting still. They can't sit still. Quantum mechanics absolutely forbids it. According to the Heisenberg uncertainty principle, one of the foundational rules of quantum physics, you can't simultaneously know a particle's exact position and its exact momentum. The more precisely you know where a particle is, the less precisely you know how fast it's moving, and vice versa. This isn't a limitation of our instruments. It's a fundamental property of nature itself. No technology, no matter how advanced, could ever overcome it. Since quarks are confined to such a tiny space, roughly 1 femtometer across, their positions are extremely well defined. This means their momenta must be very uncertain, which in practice means the quarks are moving incredibly fast, at speeds approaching the speed of light. The quarks inside a neutron are not calm. They're racing around at relativistic speeds, confined in a prison smaller than an atom's nucleus, buffeted by gluons, surrounded by virtual particle pairs appearing and vanishing. It's absolute chaos, controlled chaos held in check by the most powerful force in nature, but chaos nonetheless. And yet, from the outside, the neutron looks perfectly calm. It has a well-defined mass, a well-defined size, no electric charge, and a specific quantum property called spin. It behaves as a single coherent object. This is one of the great magic tricks of physics. Take 3 quarks trapped in a maelstrom of gluons and virtual particles, all moving at nearly the speed of light in a space too small to see even with the most powerful microscopes. And the result is something that behaves like a single, simple, stable particle. From the outside, you'd never know the pandemonium happening within. This brings us to something important. The neutron has a property called spin, and its spin value is 1/2. This makes it a fermion, a class of particles that includes electrons and quarks and protons. Spin is an intrinsic quantum mechanical property that every particle possesses. It's not really the neutron physically spinning like a top, though the analogy is sometimes used to give people a rough picture. It's a fundamental property built into the particle at the deepest level, one that affects how the particle behaves in magnetic fields and how it interacts with other particles. The neutron has no electric charge, so you might think it shouldn't be affected by magnetic fields. But it is. The neutron has a magnetic moment. This was one of the early clues that the neutron was not a fundamental particle. If it were truly an empty, neutral, featureless ball, it wouldn't have a magnetic moment. But it does, because inside it, charged quarks are moving. Those moving charges create tiny magnetic fields. The net effect of all these internal moving charges gives the neutron a measurable magnetic moment. This magnetic moment was measured experimentally, and it matched the predictions of the quark model beautifully. The neutron's magnetic moment is about -1.91 nuclear magnetons. The negative sign means it points opposite to what you'd naively expect, which is a direct consequence of the arrangement and motion of the quarks inside. Similarly, the neutron has a charge distribution even though its total charge is 0. The interior of the neutron has regions that are slightly positive and regions that are slightly negative. The positive charge tends to be near the center, while the negative charge is distributed more toward the outside. This internal charge distribution has been mapped through electron scattering experiments, where physicists shoot electrons at neutrons and carefully measure how they bounce off. The scattering pattern reveals the distribution of charge inside, much like you could map the interior of a dark room by throwing tennis balls and listening to where they bounce. These experiments have confirmed the quark model's predictions in extraordinary detail. So let's take stock of where we are. We start with the simple picture from school. The neutron is a neutral particle sitting in the nucleus. Now we know the truth. The neutron is a composite particle made of 2 down quarks and 1 up quark. These quarks are bound together by the strong nuclear force, carried by gluons that themselves carry color charge and interact with each other. The interior of the neutron is a violent dynamic environment where quarks race at near light speed through a sea of virtual particles and gluons. Almost all of the neutron's mass comes not from the quarks themselves, but from the energy of the strong force binding them. The neutron has internal structure, including a charge distribution and a magnetic moment, both of which arise from the arrangement and motion of its constituent quarks. The neutron is not what you thought it was. It's not a simple thing. It's not a featureless ball. It's not a fundamental building block. It's a complex, dynamic, composite system held together by the most powerful force in nature. And this matters because what happens next in our story depends entirely on understanding this internal structure. Because when a neutron finds itself alone, outside the protective environment of an atomic nucleus, something goes wrong. Something fundamental. The neutron begins to fall apart. And the way it falls apart, the specific mechanism by which it decays, involves a transformation happening at the deepest level. A transformation of one of those quarks inside the neutron into a different kind of quark. This transformation is governed not by the strong force that holds the neutron together, but by a completely different force of nature. A force so feeble compared to the strong force that it seems almost absurd that it could have any effect at all. And yet it does. It destroys the neutron. And in doing so, it creates something new. But to understand how that happens, we need to leave the strong force behind for a moment and enter the domain of the weak force. A force that is subtle, slow, and strange in ways that make even the strong force seem straightforward by comparison. So now we know what a neutron really is. It's not a simple thing, it's a composite system, 3 quarks bound together by the most powerful force in nature, surrounded by a churning sea of gluons and virtual particles, almost all of its mass coming not from the quarks themselves, but from the sheer energy of the strong force holding everything together. From the outside, it looks like a calm, neutral particle. On the inside, it's a storm. But here's where the story takes a turn. Because as powerful as the strong force is, as tightly as it grips those 3 quarks, it cannot protect the neutron from everything. There is another force at work in the universe. A force so feeble, so subtle, so slow compared to the strong force that it almost seems like it shouldn't matter at all. If the strong force is a raging hurricane, this other force is a single breath of wind on a calm day. And yet this quiet, almost invisible force can do something the strong force cannot prevent. It can reach inside the neutron and change one of its quarks into a different kind of quark. And when that happens, the neutron ceases to exist. It transforms into something else entirely. This force is called the weak nuclear force, and it is responsible for one of the most important processes in all of physics, the death of a free neutron. Let's set the scene. Imagine you could somehow take a single neutron and pull it out of an atomic nucleus. Just pluck it free and set it down in empty space, all by itself. No other particles around, no nucleus to shelter inside. Just one lone neutron floating in the void. What happens? For a little while, nothing visible. The neutron sits there, apparently stable. The strong force is still holding its 3 quarks together. The gluons are still doing their job. Everything inside the neutron is still churning away just as before, but a clock has started ticking. Because that free neutron is no longer stable. It has a half-life of approximately 10 minutes and 11 seconds. That means if you start with a large collection of free neutrons, after about 10 minutes and 11 seconds, roughly half of them will have decayed. After another 10 minutes and 11 seconds, half of the remaining ones will have decayed. And so on. Each individual neutron doesn't know exactly when it will decay. Quantum mechanics makes the exact moment unpredictable for any single particle. But statistically, the average lifetime is about 14 minutes and 42 seconds. And the half-life is about 10 minutes and 11 seconds. 10 minutes. Think about that for a moment. You could boil a pot of water in 10 minutes. You could walk to the corner store and back. You could listen to 2 or 3 songs on your phone. You could make a sandwich, eat it, and clean up the plate. In that time, a neutron left on its own has a 50-50 chance of ceasing to exist. This is not a long-lived particle that gradually wears down over millions of years, like a radioactive element buried in the Earth. This is a particle that falls apart in roughly the time it takes to make a cup of coffee. For something that makes up about half of all the ordinary matter in the universe, that's a remarkably, almost shockingly short lifespan. So what exactly happens when a free neutron decays? This is where we need to go deep. We need to look inside the neutron and watch the process unfold at the quark level, because that's where the real action takes place. Remember, the neutron is made of 2 down quarks and 1 up quark. When the neutron decays, one of its down quarks undergoes a transformation. It changes its flavor. It stops being a down quark and becomes an up quark. This is not a gradual process. The down quark doesn't slowly morph into an up quark over time. It happens at a single point, a single event, a single moment where one type of quark becomes another. Before the event, you have a down quark with an electric charge of -1/3. After the event, you have an up quark with an electric charge of +2/3. Now, this creates an immediate problem. Electric charge must be conserved. This is one of the most fundamental laws in all of physics. You cannot create or destroy electric charge. It must always balance. Before the transformation, the down quark had a charge of -1/3. After the transformation, the up quark has a charge of +2/3. That's a change of +1. Where did that extra positive charge come from? The answer is that the down quark, at the moment of its transformation, emits a particle. A very special and very heavy particle called the W- boson. The W- boson carries away exactly 1 unit of negative charge, which accounts for the difference. The down quark goes from -1/3 to +2/3, a change of +1, and the W- boson carries away -1. The books balance. Charge is conserved. The W- boson is the carrier of the weak nuclear force. Just as photons carry the electromagnetic force and gluons carry the strong force, the W and Z bosons carry the weak force. There are 3 weak force carriers in total: the W+ boson, the W- boson, and the Z boson. The W+ has a positive charge. The W- has a negative charge. The Z boson is neutral. In neutron decay, it's the W- boson that does the work. But here's something cruel about the W- boson. It is extraordinarily heavy. The W boson has a mass of about 80.4 giga-electron-volts. To put that in perspective, that's roughly 85 times heavier than the proton itself. 85 times heavier than the entire neutron that produced it. This is like a house cat giving birth to an elephant. How can a neutron, which has a mass of only about 0.94 giga-electron-volts, produce a particle that weighs 85 times more than itself? This seems to flagrantly violate the conservation of energy. You simply can't get more mass out of a process than you put in. At least, not in the classical world where everyday rules apply. But quantum mechanics has a loophole. It's called the Heisenberg uncertainty principle, and we already encountered it when talking about quark confinement. But here it shows up in a different form. There is an energy-time version of the uncertainty principle that says you can borrow energy from the vacuum, essentially creating energy out of nothing, as long as you pay it back quickly enough. The more energy you borrow, the faster you have to pay it back. You can borrow a small amount of energy for a relatively long time, or you can borrow an enormous amount of energy for an incredibly short time. The W- boson is created through this borrowing mechanism. The neutron doesn't actually have enough energy to create a real, stable W boson. Instead, the W boson exists as what physicists call a virtual particle. It pops into existence with borrowed energy, exists for an unimaginably brief instant, and then decays before the energy debt comes due. How brief? The W boson exists for roughly 3 × 10 to the minus 25 seconds. That's a decimal point followed by 24 zeros and then a 3. To call this a fleeting existence is the understatement of the century. Light itself, traveling at 300,000 kilometers per second, would cover less than 1/10 of the diameter of a proton in that time. The W boson barely exists at all. It appears, does its job, and vanishes almost before it has begun. And what does the W- boson do in that impossibly brief moment of existence? It decays. It falls apart into 2 particles, an electron and an electron antineutrino. The W- boson has a negative charge. The electron that comes out also has a negative charge of -1. The antineutrino has no charge at all. So charge is conserved again. The W boson's negative charge is carried away entirely by the electron. The antineutrino carries away energy and momentum, but no electric charge. Let me walk through the entire process one more time because it's important to see it clearly. You start with a free neutron. Inside it are 2 down quarks and 1 up quark. One of the down quarks emits a virtual W- boson and transforms into an up quark. The neutron now has 2 up quarks and 1 down quark. That's a proton. The W- boson, existing for only the tiniest fraction of a second, decays into an electron and an electron antineutrino. The final result is that where you once had a single neutron, you now have 3 separate particles: a proton, an electron, and an electron antineutrino. The neutron is gone, completely gone, replaced by 3 other particles that fly apart from each other. This process is called beta decay. Specifically, it's called beta- decay. The name comes from the early days of nuclear physics, when scientists observed 3 types of radiation coming from unstable atomic nuclei, and named them alpha, beta, and gamma, using the first 3 letters of the Greek alphabet. The beta radiation turned out to be electrons, so beta decay is the process that produces those electrons. The minus in beta minus refers to the fact that the emitted particle is negatively charged. An electron, as opposed to beta plus decay, which involves a positron, the antimatter counterpart of the electron. But we'll focus on beta minus decay here because that's what the free neutron does. Now, let's talk about the weak force itself, because understanding it is essential to understanding why this process happens the way it does. The weak force is one of the 4 fundamental forces of nature, alongside gravity, electromagnetism, and the strong force, but it's radically different from the others in several important ways. First, as its name suggests, it's weak. At the energy scales relevant to neutron decay, the weak force is roughly 1,000,000 times weaker than the strong force, and about 1,000 times weaker than the electromagnetic force. That's why neutron decay is slow. 10 minutes might not seem slow in human terms, but in the world of particle physics, it's an eternity. Strong force interactions happen in about 10 to the minus 23 seconds. That's a billionth of a trillionth of a trillionth of a second. Electromagnetic interactions are a bit slower, but still incredibly fast. The weak force, by contrast, operates on timescales that are billions and billions of times longer. A free neutron lasting 10 minutes before decaying is like a candle lasting a billion years in strong force terms. The weak force is just that sluggish. Second, the range of the weak force is fantastically short, even shorter than the strong force, while the strong force operates over distances of about 1 femtometer. The weak force operates over distances roughly 1,000 times smaller, about 1 to 3 atometers, which is on the order of 10 to the minus 18 meters. This incredibly short range is directly related to the enormous mass of the W and Z bosons. In quantum field theory, the range of a force is inversely related to the mass of the particle that carries it. Photons are massless, so electromagnetism has infinite range. Gluons are also massless in principle, though confinement effectively limits their range. But the W and Z bosons are among the heaviest particles in the Standard Model. Their enormous mass limits the weak force to an incredibly tiny range. You have to be extraordinarily close for the weak force to have any effect at all. Third, and this is the most remarkable thing about the weak force, it is the only force in nature that can change the flavor of a quark. The strong force can't do this. It binds quarks together with extraordinary power, but it doesn't change what kind of quark they are. A down quark interacting with gluons remains a down quark. The electromagnetic force can't do it either. An electron emitting or absorbing a photon is still an electron afterward. But the weak force can take a down quark and turn it into an up quark. It can take a strange quark and turn it into an up quark or a charm quark. It can transform one type of particle into a fundamentally different type of particle. No other force in nature has this ability. The weak force is the only shapeshifter in the universe. It is the only mechanism in all of known physics that can change one flavor of quark into another. Without it, quarks would be stuck as whatever flavor they were born. The universe would be a static, frozen place where matter could never transform from one type to another at the fundamental level. This ability to change quark flavors is why the weak force is responsible for so many important processes in nature. Without it, stars couldn't shine. The sun's fusion process depends on the weak force converting protons into neutrons at a critical step. We'll see exactly how that works later. But the point is this: the weak force is the only force that can change one type of quark into another, and that makes it essential to virtually every nuclear transformation in the universe. But let's come back to our free neutron. We've described what happens when it decays. Now let's talk about why it decays. What drives this process? The fundamental answer is energy. The neutron is slightly heavier than the proton. The neutron's mass is about 939.565 mega electron volts. The proton's mass is about 938.272 mega electron volts. The difference is about 1.293 mega electron volts. That's a tiny difference, only about 1/10 of 1%. But it's enough. Nature always seeks the lowest energy state. A ball on a hillside will roll downhill. A hot object will radiate heat until it cools to the temperature of its surroundings. And a particle that can transform into a lighter particle will eventually do so, as long as there's a force that allows the transformation. The neutron is heavier than the proton. The weak force allows the transformation. So the neutron decays. That mass difference of 1.293 mega electron volts is converted into the kinetic energy of the decay products. It becomes the energy of the electron, the anti-neutrino, and the recoiling proton. The electron comes out with an average kinetic energy of a few hundred kilo electron volts. The anti-neutrino carries away some energy too, and the proton recoils slightly, taking a small amount of kinetic energy. The total energy of all the products, including their rest masses, exactly equals the original rest mass of the neutron. Energy is conserved perfectly. But here's something subtle that's worth pointing out. The mass difference between the neutron and proton is incredibly small. 1.293 mega electron volts out of a total mass of about 940 mega electron volts. That's like the difference between two people who each weigh about 200 pounds, where one person weighs just a few ounces more than the other. You'd never notice the difference by looking at them. And yet, that tiny difference is the entire reason the free neutron is unstable. If the neutron were just slightly lighter, if the mass difference went the other way, then the proton would be the unstable one, and the neutron would be stable. The consequences of that would be staggering. If protons decayed instead of neutrons, hydrogen atoms would be unstable because a hydrogen atom is just one proton with one electron. Chemistry as we know it wouldn't exist. Stars wouldn't form the way they do. The universe would be radically different. The fact that the neutron is slightly heavier than the proton by this razor-thin margin is one of those cosmic coincidences that makes the universe as we know it possible. Now, you might wonder where this mass difference comes from. Why is the neutron slightly heavier? After all, both particles are made of up and down quarks. The proton has 2 up quarks and 1 down. The neutron has 2 down quarks and 1 up. The down quark is slightly heavier than the up quark. The up quark has a mass of roughly 2.2 mega electron volts. The down quark has a mass of roughly 4.7 mega electron volts. Since the neutron has 2 down quarks instead of 1, and the proton has 2 up quarks instead of 1, the neutron contains more quark mass. But remember, the quark masses account for only about 1% of the total mass. Almost all the mass comes from the strong force energy. So the strong force contributions also differ slightly between the proton and neutron, partially because the electromagnetic interactions between the quarks differ. The proton's quarks have a combined charge of +1, while the neutron's quarks have a combined charge of 0. The electromagnetic energy stored in these different charge configurations is slightly different. It turns out that the electromagnetic contribution would actually make the proton heavier than the neutron, because squeezing more electric charge into a small space takes energy. But the quark mass difference wins out. The down quark being heavier than the up quark makes the neutron heavier overall, despite the electromagnetic effect working in the opposite direction. The final result is that the neutron is heavier by 1.293 mega electron volts. It's a delicate balance between the quark masses and the electromagnetic energy, and it just barely tips in the direction that makes the neutron heavier. Let me tell you about the anti-neutrino because it's a fascinating particle, and it plays a crucial role in this story. The electron anti-neutrino emitted during neutron decay is an antimatter particle. It's the antiparticle of the electron neutrino. Neutrinos are among the most ghostly particles in nature. They have almost no mass. For decades, physicists thought they might be completely massless, but experiments in the late 1990s and early 2000s showed that neutrinos do have a tiny mass, although we still don't know exactly how much. The best measurements put the neutrino mass at less than about 1 electron volt, which is more than 1,000,000 times lighter than an electron. Neutrinos also interact only through the weak force and gravity. They don't feel the strong force at all. They don't feel the electromagnetic force because they have no electric charge. The only forces that affect them are gravity, which is negligibly weak for something so unbelievably light, and the weak force, which, as we've discussed, has that incredibly tiny range of about 1,000th of a femtometer. This means neutrinos barely interact with anything. They can pass through matter almost as if it weren't there. Right now, as you listen to this, about 65 billion neutrinos from the sun are passing through every square centimeter of your body every single second. They're going through you, through the earth beneath you, through the planet and out the other side, and almost none of them interact with anything along the way. A neutrino could travel through a wall of solid lead 1 light year thick and have about a 50-50 chance of passing through without hitting a single atom. That's how weakly neutrinos interact with matter. They're like ghosts, passing through the physical world without leaving a trace. The existence of the neutrino was actually predicted before it was observed. In the early 20th century, physicists studying beta decay noticed something troubling. When a neutron decayed into a proton and an electron, the energies didn't add up. If the neutron simply decayed into a proton and an electron, the electron should always come out with the same energy, determined by the mass difference between the neutron and the proton. But experiments showed that the electron came out with a range of energies, from nearly 0 up to a maximum value. Some electrons came out fast, others came out slow. Energy seemed to be disappearing. This was a genuine crisis in physics. Energy conservation was one of the most sacred principles. If it failed at the subatomic level, the consequences for all of physics would be devastating. Some physicists, including the great Niels Bohr, seriously suggested that maybe energy conservation didn't apply at the subatomic level. Maybe the rules broke down inside the atom. Maybe the quantum world simply didn't follow the same bookkeeping as the macroscopic world. It was a radical proposal, and many physicists found it deeply troubling. But in 1930, a physicist named Wolfgang Pauli proposed a different solution. He suggested that a third particle was being emitted alongside the electron, a particle that was electrically neutral, extremely light, and almost impossible to detect. This invisible particle was carrying away the missing energy. Sometimes it took a lot of energy, leaving the electron with little. Sometimes it took only a little energy, leaving the electron with a lot. The varying distribution of energy between the electron and this mystery particle explained why the electron's energy wasn't fixed. Pauli called his proposed particle the neutron, but when James Chadwick discovered the actual neutron in 1932, the name was already taken. So Enrico Fermi renamed Pauli's particle the neutrino, which is Italian for little neutral one. The neutrino wasn't directly detected until 1956, 26 years after Pauli predicted it. Clyde Cowan and Frederick Rains finally observed neutrinos coming from a nuclear reactor and confirmed their existence. Rayan received the Nobel Prize for this work in 1995. Pauli never won the Nobel for his neutrino prediction, though he won it for other work. So the full picture of neutron decay is this: a free neutron made of 2 down quarks and 1 up quark undergoes a weak interaction. 1 down quark emits a virtual W- boson and transforms into an up quark. The neutron becomes a proton. The virtual W- boson almost instantly decays into an electron, and an electron antineutrino. The proton, electron, and antineutrino share the energy released by the mass difference between the neutron and the proton. The electron and antineutrino fly away at high speed. The proton recoils gently, and the neutron is gone. This process is happening constantly in nature, all around us, all the time. Free neutrons are produced in nuclear reactions, in particle collisions, in cosmic ray interactions with the atmosphere, in nuclear reactors, and in supernova explosions. And every single free neutron that's produced, if it isn't captured by a nucleus, within about 10 minutes, will decay through this exact process. A down quark becomes an up quark. A W boson appears and vanishes in a flash too brief to measure. An electron and an antineutrino are born into the universe, and a neutron dies. But here is the key point that we need to emphasize before we move forward. This is a free neutron phenomenon. This is what happens to a neutron that is alone, outside an atomic nucleus, with no other nucleons around it. A neutron floating in empty space, unbound, solitary. That neutron is doomed. It cannot survive. The weak force will find it, reach inside it, change one of its quarks, and destroy it. 10 minutes is all it gets. But neutrons inside atomic nuclei are a completely different story. Right now, inside your body, there are roughly 7 times 10 to the 27th neutrons. That is 7 billion billion neutrons. They're inside the nuclei of the carbon, nitrogen, oxygen, calcium, iron, and every other element that makes up your flesh and bones and blood. Those neutrons have been inside those nuclei for billions of years. Some of them have been bound inside stable nuclei since before the Earth was formed, since before the sun ignited, since the ancient stars that forged those elements exploded and scattered their contents across space. Those neutrons are not decaying. They're not falling apart. They're not transforming. They're not dying. They're perfectly, completely stable. The same particle that can't last 10 minutes alone has been sitting comfortably inside nuclei for longer than our solar system has existed. How is this possible? How can the same particle be violently unstable in one context and perfectly stable in another? The answer has to do with energy, with the environment the neutron finds itself in, and with a concept called binding energy. And this is what we need to understand next. Because the difference between a neutron that lives for 10 minutes and a neutron that lives for billions of years is not a difference in the neutron itself. It's a difference in where the neutron is. Context is everything. The same particle with the same quarks, the same gluons, the same internal structure can be mortal or immortal, depending on whether it's alone or surrounded by other nucleons inside a nucleus. And understanding why that is the case reveals something deep about how nature works. So we've arrived at a paradox. A free neutron left alone in empty space decays in about 10 minutes. The weak force reaches inside, changes a down quark into an up quark, and the neutron transforms into a proton, an electron, and an antineutrino. It's gone, destroyed. A particle that makes up roughly half the mass of every atom heavier than hydrogen, and it can't even survive 10 minutes on its own. And yet, right now, inside the atoms that make up your body, there are billions upon billions of neutrons that have been stable for longer than the Earth has existed. The neutrons inside the iron. Atoms in your blood were forged in the core of a massive star that exploded as a supernova more than 4.5 billion years ago. Those neutrons have been sitting inside iron nuclei ever since, through the formation of the solar system, through the cooling and solidifying of the Earth, through the origin of life, through billions of years of evolution, through the rise of every civilization, through every moment of human history. Those neutrons have been there the entire time, perfectly stable, showing no signs whatsoever of decay. The same particle, the same internal structure, the same 2 down quarks and 1 up quark, the same gluons, the same churning sea of virtual particles. Everything about the neutron itself is identical whether it's free or bound inside a nucleus. And yet in one case it lives for 10 minutes, and in the other it lives for billions of years, potentially forever. How? How can the same particle be fatally unstable in one situation and essentially immortal in another? The answer is one of the most elegant and important concepts in all of physics. It's called binding energy. And understanding it requires us to think carefully about what it means for particles to be bound together inside a composite system versus existing freely on their own. Let's start with something familiar. Imagine you're standing at the bottom of a deep well. You want to get out to climb up to ground level. To do that, you need energy. You need to climb, which requires effort, which requires energy. If you don't have enough energy to climb all the way up, you're stuck. You can't escape. Now, let's say you're standing at the bottom of the well and someone lowers a ball down to you. The ball is at the bottom of the well with you. If you want to throw the ball up and out of the well, you need to throw it hard enough to cover the full height of the well. If you don't throw it hard enough, it comes back down. It doesn't have enough energy to escape. This is analogous to what happens inside an atomic nucleus. The neutrons and protons inside a nucleus are sitting in an energy well. The strong nuclear force has pulled them together and locked them in place, and in doing so, it has lowered their total energy. To get a neutron out of the nucleus to free it, you'd have to put energy back in. You'd have to supply enough energy to climb out of the well. The amount of energy you need to supply is the binding energy. Here's the key insight. When neutrons and protons come together to form a nucleus, the strong nuclear force binds them together so tightly that the total mass of the nucleus is actually less than the combined masses of all the individual protons and neutrons that make it up. Let me say that again because it's counterintuitive. If you take a helium-4 nucleus, which contains 2 protons and 2 neutrons, and you weigh it, it weighs less than 2 free protons and 2 free neutrons weighed separately. The difference is about 28.3 mega electron volts. That's the binding energy. It's the energy that was released when those 4 particles came together, and it's the energy you'd need to put back in to take them apart. This mass difference is real and measurable. It's not some theoretical abstraction. If you put 2 free protons and 2 free neutrons on one side of an incredibly precise scale, and a helium-4 nucleus on the other, the helium nucleus would weigh less. The missing mass has been converted into energy, the energy that was released when the nucleus formed, in accordance with Einstein's E equals mc squared. The binding energy manifests as a real, measurable reduction in mass. Now, here's how this relates to neutron decay. Remember, a free neutron decays because it's heavier than a proton. The mass difference is 1.293 mega electron volts. That mass difference is what drives the decay. The neutron can transform into a proton because doing so releases energy. The neutron rolls downhill, energetically speaking, into the lower mass proton state, and the released energy becomes the kinetic energy of the electron and antineutrino. But inside a nucleus, the situation is completely different. The neutron is bound. It's sitting in that energy well created by the strong force. Its effective energy has been lowered by the binding energy. To decay, the neutron would need to transform into a proton while remaining inside the nucleus. But the proton it would become is also inside the nucleus. And the nucleus has specific energy levels, specific quantum states that the proton can occupy. In a stable nucleus, all the available proton energy levels that the new proton could occupy are at a higher energy than the neutron's current state. Once you account for the binding energy and the electromagnetic repulsion between protons. Let me make this more concrete. Inside a stable nucleus like carbon-12, which has 6 protons and 6 neutrons, each neutron is bound with a certain amount of binding energy. If one of those neutrons were to decay into a proton, the new proton would have to fit into the nuclear structure. But there's a problem. Protons repel each other electromagnetically because they all carry positive charge. Adding another proton to a nucleus that already has 6 protons means the new proton faces electromagnetic repulsion from all 6 existing protons. This repulsion raises the energy cost of adding the proton. Furthermore, protons and neutrons are fermions, which means they obey the Pauli exclusion principle. No 2 identical fermions can occupy the same quantum state. The proton energy levels in carbon-12 are already partially filled. The new proton would have to go into a higher energy level. When you add up all these effects, the binding energy holding the neutron in place, the electromagnetic repulsion the new proton would face, and the requirement that the new proton occupy a higher energy level, the result is that the decay would require more energy than the 1.293 mega electron volts that the neutron to proton mass difference provides. The neutron simply doesn't have enough energy to decay. It's as if the neutron is at the bottom of a well and the proton state is at the top of a nearby hill. In free space, the proton state is slightly lower in energy, so the neutron rolls downhill into it. But inside the nucleus, the binding energy changes the landscape. It raises the proton state relative to the neutron state, or equivalently, it lowers the neutron state relative to the proton state. Either way, the neutron can no longer roll downhill. It's trapped, it's stable. This is the fundamental difference between a free particle and a bound particle. A free neutron exists in a simple energy landscape where the proton state is lower and decay is energetically favorable. A bound neutron exists in a complex energy landscape shaped by binding energy, electromagnetic forces, and quantum mechanical rules where decay may no longer be energetically possible. The neutron itself hasn't changed. Its quarks are the same. Its gluons are the same. Its internal structure is identical. What's changed is its environment. It's context, the energy landscape it sits in. And that context makes all the difference between life and death. This principle, that the behavior of a particle depends on its environment, on whether it's free or bound inside a composite system, is one of the most important ideas in nuclear physics. It's not unique to neutrons. It applies to any particle that can exist in different energy states, depending on its surroundings. But the neutron provides the most dramatic example, because the difference in outcomes is so stark. 10 minutes versus billions of years. Decay versus perfect stability, all determined by context. Now, let's go deeper into how the strong nuclear force creates this binding energy in the first place. Inside the neutron and the proton, the strong force operates through gluon exchange between quarks. But when we zoom out to the scale of the entire nucleus, something interesting happens. The quarks and gluons inside one proton or neutron don't directly interact with the quarks and gluons inside a neighboring proton or neutron in a simple way. The strong force between quarks is confined within each individual nucleon, but there's a residual effect. Think of it this way. A neutral atom has no net electric charge, but it can still attract other neutral atoms through what are called van der Waals forces, residual electromagnetic effects that arise because the positive and negative charges inside each atom are slightly distributed in space. Something similar happens with the strong force. Even though each proton and neutron is color neutral, the strong force leaks out slightly, creating an attractive residual force between nearby nucleons. This residual strong force, sometimes called the nuclear force, is what holds the nucleus together. The nuclear force between nucleons is carried by particles called pions, which are quark-antiquark pairs. These pions are constantly being exchanged between protons and neutrons in the nucleus. A proton emits a pion and briefly becomes a neutron. The pion is absorbed by a neighboring neutron, which briefly becomes a proton. This exchange happens continuously and rapidly, creating an attractive force that binds the nucleons together. It's a bit like two people tossing a ball back and forth. The exchange of the ball creates a bond between them, keeping them connected. This nuclear force is strong, but it has limitations. It's attractive at distances of about 1 to 2 femtometers, but it becomes repulsive at very short distances, less than about half a femtometer. This repulsive core prevents nucleons from collapsing into each other. It's what gives the nucleus its finite size. The nuclear force also has a very short range. Beyond about 2 to 3 femtometers, it drops to essentially 0. This means each nucleon in a nucleus only feels the nuclear force from its nearest neighbors, not from nucleons on the other side of the nucleus. This short range of the nuclear force has profound consequences for nuclear stability. In small nuclei, every nucleon is close to every other nucleon. They all feel each other's attractive nuclear force. The binding energy per nucleon increases as you add more nucleons to these small nuclei. Helium-4, with its 2 protons and 2 neutrons, has a binding energy of about 7.1 megaelectron volts per nucleon. Carbon-12 has about 7.7 megaelectron volts per nucleon. Iron-56 has about 8.8 megaelectron volts per nucleon. Iron-56 sits at or very near the peak of what physicists call the binding energy curve, with only nickel-62 edging slightly above it. But for nuclei larger than iron, something changes. As you add more protons, the electromagnetic repulsion between them increases. And because the electromagnetic force has infinite range, unlike the nuclear force which only reaches nearby neighbors, every proton in the nucleus repels every other proton regardless of distance. For large nuclei, this cumulative electromagnetic repulsion starts to compete with the nuclear binding force. The binding energy per nucleon begins to decrease. Uranium-238, one of the heaviest naturally occurring nuclei, has a binding energy of only about 7.6 mega-electron volts per nucleon. That's less than iron. This is why very heavy nuclei tend to be unstable. The electromagnetic repulsion is winning the battle against the nuclear force. This brings us the neutron to proton ratio, one of the most important factors in nuclear stability. For light nuclei, the most stable configuration tends to have roughly equal numbers of protons and neutrons. Helium-4 has 2 of each. Carbon-12 has 6 of each. Oxygen-16 has 8 of each. The balance makes sense because the nuclear force is roughly the same between proton-proton, proton-neutron, and neutron-neutron pairs. Having equal numbers maximizes the binding while the electromagnetic repulsion from the protons is still manageable. But as nuclei get heavier, something shifts. The electromagnetic repulsion between protons grows because there are more protons repelling each other. To compensate, nature adds extra neutrons. Neutrons contribute to the nuclear binding through the strong force, but they don't add to the electromagnetic repulsion because they have no charge. Extra neutrons act as a kind of nuclear glue, providing additional attractive force without the cost of additional repulsion. This is why heavy nuclei have significantly more neutrons than protons. Iron-56 has 26 protons and 30 neutrons. Tin-120 has 50 protons and 70 neutrons. Lead-208, one of the heaviest stable nuclei, has 82 protons and 126 neutrons. The neutron excess grows as nuclei get heavier, but there's a limit to how much neutrons can help. If you add too many neutrons, the nucleus becomes unstable for a different reason. The Pauli exclusion principle forces each additional neutron into a higher and higher energy state. At some point, these high-energy neutrons have enough energy to decay into protons through beta decay, even inside the nucleus. The binding energy is no longer sufficient to prevent the decay. When this happens, the nucleus is radioactive, it's unstable, and it will undergo beta decay, with a neutron inside the nucleus converting into a proton, emitting an electron, and an antineutrino. This is crucial to understand. Beta decay doesn't only happen to free neutrons. It also happens inside nuclei, but only inside unstable nuclei. Nuclei that have too many neutrons relative to the optimal ratio. In these nuclei, the energy landscape has shifted. The binding energy can no longer fully compensate for the neutron-proton mass difference. A neutron inside the nucleus has enough energy to transform into a proton, so it does. The nucleus changes identity. A nucleus with too many neutrons will undergo beta minus decay, converting a neutron into a proton and moving closer to the optimal neutron to proton ratio. Carbon-14 is a classic example. It has 6 protons and 8 neutrons. The stable form of carbon is carbon-12 with 6 protons and 6 neutrons. Carbon-14 has 2 extra neutrons, making it unstable. It undergoes beta decay with a half-life of about 5,730 years. One of its neutrons converts into a proton, and the carbon-14 becomes nitrogen-14, which has 7 protons and 7 neutrons. Nitrogen-14 is stable. The excess neutron energy found a way out through the weak force, and the system settled into a more stable configuration. This is the basis of radiocarbon dating. Living organisms constantly take in carbon from the environment, including a small proportion of carbon-14 created by cosmic rays in the atmosphere. When the organism dies, it stops taking in new carbon. The carbon-14 already in its body begins to decay. By measuring how much carbon-14 remains in a sample, scientists can determine how long ago the organism died. This technique has been used to date archaeological artifacts, ancient bones, old textiles, and countless other objects up to about 50,000 years old. All of it works because neutrons inside carbon-14 nuclei are unstable, slowly decaying through the weak force over thousands of years. Now contrast carbon-14 with carbon-12. Carbon-12 has 6 protons and 6 neutrons. It's perfectly stable. The neutrons inside carbon-12 will never decay. They can't. The energy balance doesn't permit it. Those neutrons are bound so securely that the weak force has no room to act. They will sit in that nucleus effectively forever, or at least until something external comes along and breaks the nucleus apart. There's another type of instability worth mentioning that goes in the opposite direction. Some nuclei have too many protons relative to neutrons. In these cases, a proton inside the nucleus can convert into a neutron through a process called beta plus decay or positron emission. This is the reverse of what happens in free neutron decay. A proton's up quark emits a W plus boson and converts into a down quark. The proton becomes a neutron. The W plus boson decays into a positron, the antimatter counterpart of the electron, and an electron neutrino. This only happens inside nuclei where the energy conditions allow it. A free proton, as far as we know, is perfectly stable. It doesn't decay. The proton is lighter than the neutron, so it can't decay into a neutron in free space because that would require energy to be added. But inside a proton-rich nucleus, the binding energy and electromagnetic energy can shift the balance enough that a proton can transform into a neutron. Once again, context determines behavior. So let's step back and see the full picture. Nature has a preferred configuration for each nucleus, a specific ratio of protons to neutrons that minimizes the total energy. If a nucleus has too many neutrons, it will undergo beta minus decay. Neutrons transform into protons until the ratio is right. If a nucleus has too many protons, it will undergo beta plus decay or electron capture. Protons transform into neutrons until the ratio is right. And if the nucleus already has the right ratio, if it's at or near the minimum energy state, then neither process is energetically favorable. The neutrons stay as neutrons. The protons stay as protons. The nucleus is stable, and it stays stable for billions of years, or effectively forever. The band of stable nuclei, when plotted on a chart with the number of protons on one axis and the number of neutrons on the other, forms a narrow line called the Valley of Stability. Nuclei in this valley are stable. Nuclei on either side of the valley are radioactive. Those with too many neutrons undergo beta minus decay, moving toward the valley. Those with too many protons undergo beta plus decay or electron capture, also moving toward the valley. Nature always seeks the valley. It always rolls downhill toward the most stable configuration. There are about 252 nuclei that are considered observationally stable. they've never been observed to decay. They're the survivors, the nuclei that have found the perfect balance between the strong nuclear force, the electromagnetic force, and the quantum mechanical rules that govern how protons and neutrons arrange themselves. Some of these nuclei are incredibly common. Hydrogen-1, the simplest nucleus, which is just a single proton. Helium-4, carbon-12, nitrogen-14, oxygen-16, iron-56. These are the building blocks of the universe, the most abundant nuclei in existence. And every neutron inside every one of these stable nuclei is protected from decay by the binding energy that holds the nucleus together. But there's something deeply strange about this that's worth sitting with for a moment. The weak force is still there. It hasn't gone away. It's still operating inside every nucleus, including stable ones. The W boson can still theoretically interact with the quarks inside a bound neutron. The mechanism for decay still exists. The force that would cause the decay hasn't been turned off or blocked. What's happened is that the energy conditions have changed. The decay is no longer energetically allowed because the binding energy has shifted the energy landscape. The weak force is trying to cause the decay, in a sense, but it can't succeed because there isn't enough energy available for the final state to exist. It's like a ball sitting in a valley between two hills. Gravity is still pulling on the ball. The force is still there, but the ball can't roll uphill without additional energy, so it stays put. The force exists, but it has no effect because the energy landscape prevents the transition. This is a profound concept. It means that stability isn't about the absence of forces or the absence of potential decay mechanisms. Stability is about energy balance. A system is stable when there is no lower energy state available that it can transition to. The forces are all still present, still acting, still trying to cause changes, but if the energy bookkeeping doesn't work out, if the final state would require more energy than is available, then nothing happens. The system remains as it is. This is true not just for neutrons in nuclei, but for all of physics. Stability everywhere is a question of energy landscapes. Whether a rock sits on a hilltop or in a valley, whether a chemical reaction proceeds or doesn't, whether a star continues burning or collapses, in every case it's the energy balance that determines what happens. Let me give you one more way to think about this because it's so important. Imagine you have a neutron inside a helium-4 nucleus. The binding energy of that nucleus is about 28.3 mega electron volts in total, or about 7.1 mega electron volts per nucleon. For that neutron to decay, it would need to become a proton inside the nucleus. But the new proton would face electromagnetic repulsion from the two protons already there. It would need to occupy a quantum state that fits within the nuclear structure. When you work out all the energetics, the final state, the nucleus with 3 protons and 1 neutron, plus an electron and antineutrino, has higher total energy than the initial state. The helium-4 nucleus with 2 protons and 2 neutrons. The decay would require energy to be added to the system rather than releasing energy. It would be like rolling a ball uphill. It doesn't happen spontaneously. So the neutron stays. It doesn't decay. It's stable. Compare this to a free neutron. The free neutron has mass 939.565 mega electron volts. The proton has mass 938.272 mega electron volts. The electron has mass 0.511 mega electron volts. The antineutrino has essentially zero mass. The total mass of the products is about 938.783 mega electron volts. That's less than the neutron's mass by about 0.782 mega electron volts. There's energy left over. The decay releases energy. It's energetically favorable. So it happens. The neutron decays. Inside the stable nucleus, the binding energy tips the balance the other way. Outside the nucleus, there's energy to spare. Inside the nucleus, there's an energy deficit. Same neutron, same quarks, same gluons, same weak force, different energy landscape, different outcome. This is why context matters so much in physics. You cannot understand the behavior of a particle without understanding its environment. A neutron is not simply stable or unstable as an inherent, fixed property. Its stability depends entirely on what system it's part of. Strip it from a nucleus, and it dies in minutes. Leave it bound inside a stable nucleus, and it lives for the age of the universe. The particle doesn't change, the rules don't change, the forces don't change, only the context changes. And the context is everything. There's one final subtlety worth mentioning. In some radioactive nuclei, neutron decay happens very slowly. Carbon-14's half-life is 5,730 years. Potassium-40 has a half-life of 1.25 billion years. Some isotopes have half-lives of trillions of years, far longer than the current age of the universe. These nuclei are technically unstable. The energy balance slightly favors decay, but the process is incredibly slow. Because the energy available for decay is so small, the decay rate depends on how much energy is available. A lot of available energy means fast decay. A tiny amount of available energy means extremely slow decay. Free neutrons have about 0.782 mega electron volts of available energy, which gives them a half-life of about 10 minutes. Some unstable nuclei have only a few kilo electron volt of available energy, which gives them half-lives of billions of years. The physics is exactly the same, only the numbers change. This spectrum of stability, from perfectly stable to rapidly decaying, is all determined by the same principles we've discussed: binding energy, electromagnetic repulsion, the Pauli exclusion principle, the neutron to proton ratio. These factors combine to create an energy landscape that determines whether each nucleus is stable or unstable, and if unstable, how quickly it decays. It's all energy balance. It's all context. And so we've answered our question: why can a neutron survive inside a nucleus but not alone? Because the binding energy of the nucleus changes the energy landscape. It removes the energy that would otherwise be available for decay. It traps the neutron in a state where transformation is energetically forbidden. The strong force, by binding nucleons together so powerfully, creates an environment where the weak force cannot do its work. The most powerful force in nature protects the neutron from the only force that can destroy it. And it does so not by blocking the weak force directly, but simply by changing the energy balance so that decay is no longer possible. This is one of the most beautiful examples in physics of how different forces interact. The strong force doesn't fight the weak force. It doesn't overpower it in a direct confrontation. Instead, it reshapes the energy landscape so that the weak force has nothing to work with. It's a passive defense, not an active one. The strong force simply binds the nucleon so tightly that the weak force can't find enough energy to cause the transformation. And within that passive defense, neutrons find safety. They find stability. They find, in a very real sense, immortality. Not because they've become different particles, not because some fundamental property has changed, but because they found the right home. Now we know what a neutron is. We know it's a composite particle made of quarks, held together by the most powerful force in nature. We know that when it's alone, it dies. The weak force changes one of its quarks, and it transforms into a proton, an electron, and an antineutrino. We know that inside a stable nucleus, Bindy's energy changes the energy landscape, and the neutron is protected. The same particle, mortal in isolation, immortal in community. All of that is remarkable. But now we're going to do something different. We're going to zoom out, way out. Because the story of the neutron isn't just a story about quarks and forces and binding energy. It's a story about the entire universe. About why the universe looks the way it does. About why stars can burn, why atoms heavier than hydrogen exist, why chemistry is possible, and ultimately, why you exist at all. And it all traces back to a frantic race that happened in the first few minutes after the Big Bang. A race between neutron decay and the formation of the first atomic nuclei. Let's go back to the beginning. The very beginning. About 13.8 billion years ago, the universe began in an event we call the Big Bang. In its first moments, it was unimaginably hot and dense. We're talking about temperatures in the trillions of degrees. At these temperatures, matter as we know it couldn't exist. There were no atoms, no molecules, no nuclei, no protons or neutrons as stable objects. The universe was a screaming, superheated soup of fundamental particles. Quarks, leptons, gluons, photons, W and Z bosons, all of them smashing into each other at tremendous energies, constantly creating and annihilating each other in a chaotic frenzy that defies easy description. Everything was so hot that even the forces we talked about behaved differently. At sufficiently high temperatures, the electromagnetic force and the weak force merge into a single unified force called the electroweak force. The distinction between them disappears. The W and Z bosons, which at lower energies are extremely heavy, become effectively massless at these temperatures because the Higgs field behaves differently in such extreme conditions. The universe at this point was a place where the rules themselves were different from what we observe today. As the universe expanded, it cooled rapidly. Within about 1/1,000,000th of a second after the Big Bang, the temperature had dropped enough for quarks to be confined into protons and neutrons by the strong force. For the first time, individual protons and neutrons existed as distinct particles. But the universe was still incredibly hot, about 1 trillion degrees Celsius. At this temperature, protons and neutrons were constantly converting into each other through the weak force. A proton could absorb an electron and emit a neutrino, becoming a neutron. A neutron could emit an electron and an antineutrino and become a proton. These reactions happened rapidly and in both directions. For every neutron that converted into a proton somewhere converted into a neutron. The two populations were kept in equilibrium, roughly equal numbers of each. But as the universe continued to cool, something changed. Remember, the neutron is slightly heavier than the proton. That mass difference of 1.293 mega electron volts means that creating a neutron from a proton requires a small input of energy. At very high temperatures, this energy was freely available from the thermal environment. Particles had so much kinetic energy from the extreme heat that the small mass difference between protons and neutrons was insignificant. But as the temperature dropped, the available thermal energy decreased. It became slightly harder to convert protons into neutrons than the reverse. The balance began to tip. More neutrons were converting into protons than protons were converting into neutrons. By about 1 second after the Big Bang, the temperature had dropped to roughly 10 billion degrees. At this point, something critical happened. The neutrinos, which had been mediating many of the conversion reactions, decoupled from normal matter. The universe had expanded and cooled enough that neutrinos essentially stopped interacting with everything else. They flew off in all directions at nearly the speed of light, and have been traveling through the universe ever since, cooling as the universe expanded. Those neutrinos are still out there today, filling all of space, forming what cosmologists call the cosmic neutrino background, a ghostly relic of the first second of the universe's existence that we haven't yet been able to directly detect, because neutrinos interact so weakly with everything. When the neutrinos decoupled, the conversion reactions between protons and neutrons largely froze out. The ratio of neutrons to protons locked in at roughly 1 neutron for every 6 protons. This is called the freeze-out ratio, and it was determined by the temperature at which the weak interactions became too slow to keep up with the expansion of the universe. But here's the critical problem. The neutrons were now free. They were individual particles, unbound, floating in the hot plasma of the early universe. And free neutrons decay. The clock had started. Those neutrons had a half-life of about 10 minutes and 11 seconds. If nothing happened, if the neutrons weren't captured into nuclei, they would all decay into protons, every single one. And the universe would be made of nothing but protons and electrons. Pure hydrogen, no helium, no lithium, no heavier elements, no chemistry, no stars as we know them, no planets, no life. So a race began. A desperate, unconscious race between neutron decay and nucleosynthesis, the process of building atomic nuclei from protons and neutrons. A race that would determine the chemical composition of the entire universe. A race that played out not over millions or billions of years, but in the first few frantic minutes after the Big Bang. For nuclei to form, protons and neutrons need to stick together. The simplest step is for a proton and a neutron to combine into deuterium, which is a hydrogen isotope with 1 proton and 1 neutron. This is the first rung on the nuclear ladder. From deuterium, you can build heavier nuclei. 2 deuterium nuclei can fuse into helium-3 or tritium. Helium-3 and tritium can fuse into helium-4. Helium-4, with its 2 protons and 2 neutrons, is extraordinarily stable. It's the destination, the safe harbor where neutrons could be locked away and protected from decay. But there was a bottleneck, a critical one. In the first few minutes, the universe was still hot enough that photons, particles of light, had enough energy to break apart deuterium nuclei as fast as they formed. Every time a proton and neutron came together and stuck, a high-energy photon would come along almost immediately and smash them apart. It was like trying to build a sandcastle while waves kept washing it away. This is called the deuterium bottleneck, and it prevented significant nuclear building from happening until the universe had cooled enough for deuterium to survive the constant bombardment of high-energy photons. The temperature at which deuterium could finally persist was about 800 million degrees Celsius. The universe reached this temperature at roughly 3 minutes after the Big Bang. 3 minutes. By this point, some of the neutrons had already decayed. The ratio had shifted from 1 neutron per 6 protons to about 1 neutron per 7 protons. Roughly 12 to 13% of all nucleons were neutrons. The rest were protons. Once the deuterium bottleneck broke, nucleosynthesis happened fast. Within minutes, most of the remaining free neutrons were swept up into helium-4 nuclei. The process was efficient because helium-4 is so tightly bound. Its binding energy per nucleon is high enough that once formed, it's extremely difficult to break apart. The neutrons were captured, bound, protected. The weak force could no longer touch them. The decay clock stopped. By about 20 minutes after the Big Bang, nucleosynthesis was essentially over. The universe had cooled too much for nuclear fusion reactions to continue. What was left was a specific mixture of elements. About 75% hydrogen by mass, about 25% helium-4, with trace amounts of deuterium, helium-3, and lithium-7. That's it. Those are the only elements the Big Bang produced in significant quantities. Everything else, every atom of carbon, nitrogen, oxygen, iron, gold, uranium, everything heavier than lithium was made later, inside stars. Now, here's what makes this so remarkable. That 25% helium fraction, the fraction of the universe's ordinary matter that ended up as helium-4, is one of the great predictions of Big Bang cosmology. It was calculated theoretically in the 1960s and 70s by physicists like Ralph Alpher, Robert Herman, Jim Peebles, and others. They worked out the nuclear physics step by step. The expansion rate of the universe, the neutron to proton ratio at freeze-out, the timing of the deuterium bottleneck, and predicted that about 25% of ordinary matter should be helium. This was a bold prediction, made entirely from theory, from equations scrawled on chalkboards and worked through on early computers. When astronomers measured the actual helium abundance in the universe, in ancient stars, in gas clouds far from any star that might have contaminated them with heavier elements, they found almost exactly 25%. This agreement between prediction and observation is one of the most powerful pieces of evidence that the Big Bang theory is correct. And the entire calculation depends on the neutron's half-life. It depends on exactly how fast free neutrons decay. Let me show you why this matters so deeply. If the neutron's half-life were significantly shorter, say 5 minutes instead of 10, then by the time the deuterium bottleneck broke at 3 minutes, far more neutrons would have already decayed. The neutron to proton ratio would have been much lower. Fewer neutrons would have been available to build helium. The universe would have ended up with much less helium, maybe 10 or 15% instead of 25. That might not sound like a big deal, but the consequences ripple through everything that follows. Less helium means a different chemical composition for the first generation of stars. Those stars would have burned differently at different temperatures for different lifetimes, producing different quantities of heavy elements when they exploded. The entire chain of stellar evolution that eventually led to the production of carbon, oxygen and iron, the elements essential for life, would have been fundamentally altered. Perhaps fatally so. On the other hand, if the neutron's half-life was significantly longer, say 30 minutes or an hour, then fewer neutrons would have decayed before nucleosynthesis began. The neutron-to-proton ratio would have been closer to 1 to 6 instead of 1 to 7, or even higher. More helium would have formed. Perhaps 30% or more of all ordinary matter would be helium instead of hydrogen. A universe with too much helium would also be deeply problematic for the emergence of complexity. Stars forming from helium-rich gas burn hotter and faster than hydrogen-dominated stars. They have shorter lifetimes, sometimes dramatically shorter. They might not produce the same careful balance of heavy elements that our universe's stars produce. The conditions for planet formation and the development of complex chemistry might be altered in ways that are incompatible with life as we know it. Potentially, such a universe would be sterile. The neutron's half-life of about 10 minutes is, in a sense, just right. It's long enough that a substantial fraction of neutrons survive to be incorporated into helium, giving the universe the raw materials for complex chemistry. But it's short enough that not too many survived, preventing an overabundance of helium that could have disrupted stellar evolution. This is one of those cosmic balances, one of those seemingly coincidental tunings of a fundamental physical parameter that makes the universe habitable, not because someone designed it to be that way, but because if it were different, we wouldn't be here to notice. This raises a profound question. Why is the neutron's half-life what it is? Why 10 minutes and not 5 or 30 or 300? The answer lies in the details of the weak force, specifically in the mass difference between the down and up quarks, the mass of the W boson, and the coupling constant of the weak interaction. These are fundamental parameters of the standard model of particle physics, and they combine to give the neutron its specific decay rate. If any of these parameters were slightly different, the half-life would change. And if it changed enough, the universe might look very different. Let's move beyond the Big Bang and talk about how neutrons matter in the universe today. Because even after those first 20 minutes, neutrons continue to play essential roles in the cosmos. Stars are powered by nuclear fusion, the process of combining light nuclei into heavier ones, and releasing energy in the process. In the core of our Sun, hydrogen is being fused into helium through a chain of reactions called the proton-proton chain. The temperature at the Sun's core is about 15 million degrees Celsius. The pressure is about 260 billion times the atmospheric pressure on Earth's surface. Under these extreme conditions, protons are moving fast enough to overcome their mutual electromagnetic repulsion and get close enough for the nuclear force to grab them. But the first step in this chain is the most difficult and the most important. Two protons must come together and fuse into deuterium. But two protons can't simply stick together. A nucleus of two protons, helium-2, is not stable. It would fly apart almost instantly because the electromagnetic repulsion between the two positive charges is too strong for the nuclear force to overcome at that configuration. For two protons to fuse into deuterium, one of them must convert into a neutron during the collision. A proton's up quark must change into a down quark through the weak force, emitting a positron and a neutrino. This is the reverse of free neutron decay. Instead of a neutron becoming a proton becomes a neutron. And this conversion must happen at the exact moment the two protons are close enough for the nuclear force to grab them. The probability of this happening is incredibly low. Any individual pair of protons in the sun's core might wait billions of years before this reaction occurs. The sun only manages to keep burning because it contains an astronomical number of protons, about 10 to the 57th, and at any given moment, a few of them are undergoing this reaction purely by chance. The weak force is so slow, so improbable, that even in the crushing heat and density of the sun's core, this first step is the bottleneck of the entire fusion process. It's why the sun burns steadily over billions of years rather than exploding all at once. The weak force's slowness is what makes stars long-lived and stable. Without the need for a proton to convert into a neutron through the weak interaction, nuclear fusion would happen much faster. Stars would burn through their fuel in a fraction of the time. They might not last long enough for planets to form, for life to develop, for evolution to produce complex organisms. Once again, the weak force and the neutron are quietly shaping the universe. In the later stages of stellar evolution, neutrons play an even more direct role. Massive stars, those much larger than the sun, burn through their hydrogen quickly and begin fusing heavier elements. Helium fuses into carbon. Carbon fuses into neon. Neon fuses into oxygen. Oxygen fuses into silicon. Silicon fuses into iron. Each stage requires higher temperatures and produces heavier elements. Iron is the end of the line for fusion. Beyond iron, fusion no longer releases energy. It absorbs energy. A massive star with an iron core has reached a dead end. When the iron core grows too massive, typically reaching about 1.4 solar masses, it can no longer support itself against gravity. It collapses under its own weight in a fraction of a second, triggering a supernova explosion. This is one of the most violent events in the universe. The energy released in a single supernova explosion is greater than the energy our sun will produce in its entire 10 billion year lifetime. During this catastrophic event, conditions become so extreme that an enormous flood of free neutrons is produced. These neutrons bombard the iron and other nuclei present in the collapsing star. The nuclei capture the neutrons rapidly, one after another, building up to heavier and heavier elements. This is called the rapid neutron capture process, or R process. It's how the universe produces many of the heaviest elements. Gold, platinum, uranium, thorium, and dozens of other heavy elements are forged in these violent events through the capture of neutrons by existing nuclei. There's also a slower version of this process called the S process for slow neutron capture that occurs in certain types of aging stars called asymptotic giant branch stars. In these stars, free neutrons are produced at a lower rate. Nuclei capture them one at a time with enough time between captures for unstable nuclei to undergo beta decay, converting excess neutrons into protons and moving along the valley of stability before capturing more neutrons. The S process produces about half of the elements heavier than iron. The other half comes from the R process in supernovae and neutron star mergers. Speaking of neutron star mergers, these events are among the most violent and spectacular phenomena in the modern universe. Neutron stars are the collapsed remnants of massive stars that weren't quite massive enough to form black holes. They're about 12 miles across, roughly the size of a city, but they contain 1.4 to 2 times the mass of our entire sun, all compressed into that tiny volume. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. These stars are made almost entirely of neutrons, packed together so tightly that the atomic nuclei have been crushed and merged into a continuous sea of neutron matter, held together by gravity so intense that the surface escape velocity is roughly 1/3 the speed of light. When two neutron stars spiral together and collide, the event produces gravitational waves rippling through space-time, a burst of gamma rays brighter than an entire galaxy, and a cloud of neutron-rich debris that undergoes rapid nucleosynthesis, forging heavy elements and flinging them across space. In 2017, astronomers detected gravitational waves from a neutron star merger for the first time, an event called GW170817. The accompanying electromagnetic observations confirmed that these mergers produce enormous quantities of heavy elements, including gold and platinum. Much of the gold in the Earth's crust may have been forged in neutron star mergers billions of years ago, created from the same unstable particles that can't survive 10 minutes on their own. Closer to home, neutron decay and neutron interactions play a practical role in nuclear technology that affects millions of people every day. In nuclear reactors, free neutrons are the workhorses that make the entire process possible. Uranium-235 nuclei absorb a free neutron and become so unstable that they split apart in a process called nuclear fission. This splitting releases enormous amounts of energy, roughly 200 million electron volts per fission event, along with 2 or 3 more free neutrons, which go on to strike other uranium nuclei and cause more fissions in a self-sustaining chain reaction. The energy released heats water, produces steam, turns turbines, and generates electricity that powers cities and homes around the world. The free neutrons between fission events are vulnerable to decay, but in a reactor, the time between fission events is typically very short, microseconds or less, far shorter than the neutron's 10-minute half-life. So the neutrons survive long enough to sustain the chain reaction. Neutron decay also matters in medical science. Certain isotopes used in medical imaging undergo beta decay. The electrons or positrons emitted during these decays can be detected by scanners, allowing doctors to image the inside of the body. Positron emission tomography, or PET scanning, relies on isotopes that undergo beta plus decay. The positrons emitted by these isotopes annihilate with electrons in the body, producing pairs of gamma-ray photons that travel in opposite directions. Detectors surrounding the patient pick up these photon pairs and use them to construct detailed images of metabolic activity inside the body. Every PET scan that has ever helped diagnose a disease or guide a treatment owes its existence to the weak force and the process of beta decay. Now, let's reflect on what we've learned. We start with something that seemed simple: a neutron, a neutral particle in the nucleus of an atom. Something you probably learned about in school and never thought much about again. But when we looked deeper, we found something extraordinary. A particle that is anything but simple. A storm of quarks and gluons on the inside, calm and featureless on the outside. A particle that the weak force destroys in minutes when it's alone, but that the strong force shields for billions of years when it's bound inside a nucleus. a particle whose fate depends entirely on where it is. And this one particle, this unstable, fragile thing that cannot even survive 10 minutes on its own, is responsible for the structure of the universe. The neutron's half-life determined how much helium the Big Bang produced. That helium fraction shaped the first generation of stars. Neutron capture processes in those stars and in supernova explosions forged the heavy elements that make up rocky planets and living organisms. The weak force that destroys the free neutron is the same force that allows stars to burn steadily for billions of years. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood exists because neutrons were captured into nuclei at the right moment, survived in those nuclei for billions of years, and participated in the nuclear reactions that built the periodic table. You are, in a very direct sense, a product of the neutron story. The atoms in your body were forged in stars where neutrons played essential roles. Those atoms were scattered into space by supernova explosions driven by neutron physics. They drifted through interstellar space for millions of years before being swept up into the cloud of gas and dust that collapsed to form our solar system. They became part of the Earth. They became part of the oceans and the atmosphere. They were incorporated into living organisms through billions of years of chemistry and evolution. And now, they're part of you. A being made of atoms whose nuclei contain neutrons, particles that would decay in minutes if freed from those nuclei, particles that are stable only because they found the right home. There's something poetic in that. The neutron is a particle that cannot exist alone. It needs community. It needs other particles around it, bound to it by the strong force, to survive. A free neutron is doomed. A bound neutron is immortal. And from that simple distinction, from the difference between isolation and belonging, the entire complexity of the universe unfolds. The next time you look at your hand, remember what's inside it. Trillions upon trillions of neutrons, each one a seething storm of quarks and gluons, each one held stable by the binding energy of the nucleus it calls home. Each one carrying a legacy that stretches back to the first minutes after the Big Bang, when free neutrons were racing against their own decay, desperately trying to find a nucleus to shelter in before the clock ran out. The ones that made it are still here. They're in the iron in your blood, the calcium in your bones, the oxygen you're breathing right now. And the ones that didn't make it, the ones that decayed in those early minutes, became the protons that form the hydrogen in the water that covers most of our planet. The hydrogen that fuels the sun. The hydrogen that is by far the most abundant element in the universe. Either way, the neutron shaped everything. Whether it survived or decayed, whether it found shelter or fell apart, the neutron story is the universe's story. And now you know that story. You know what a neutron really is. And you know why it can't survive alone. Thank you for joining me on this journey tonight, and remember, everything around you, every atom, every molecule, every breath you take is built on the legacy of particles that can't survive 10 minutes on their own, but found a way to last forever by coming together. Good night. And the next time someone tells you the neutron is just a boring neutral particle, you'll know the truth. It's one of the most remarkable objects in the universe.